السلام عليكم ورحمة الله وبركاته. يسعد صباحكم يا شباب. طبعا رايحين نعتمد على أسلوب الفيديوهات المسجلة في حالة الطوارئ هذه. طبعا نسأل الله أنه تمر على خير وسلام. هذه الفيديوهات راح أنا أسجلها وراح أحملها على اليوتيوب وحأعمل لكم إياها تظهر على المودل دايركتلي. ممكن إذا بتحبوا تعملوا سبسكرايب على اليوتيوب يصير يظهر عندكم أسرع، بيصير برضه ما في أي مشكلة. بس حتلاقوها كلها على المودل من ناحية محاضرات. هلا من ناحية لقاءات إن شاء الله حنصير نجتمع مرة واحدة في الأسبوع، أشوف الفيدباكس منكم، وبلس نتناقش عن موضوع المحاضرة إذا في حدا مش فاهم جزئية معينة. طيب أنا هذه المحاضرة كنت already بادي فيها بس كان العدد قليل، فمش قصة كبيرة لو عدتها أو عدت الجزئية الأولى منها، لأنه كثير مهم إنه نعرف عن إيش بتحكي بداية هذا الشابتر. شغلة ثانية بالنسبة للمشروع إن شاء الله حأعمل له I will post an announcement on a Moodle, so keep posted please. Okay. راح أعرض لكم تفاصيل المشروع إن شاء الله. طيب إحنا so far we finished talking about chapter 1 and 2. Now chapter 3 again we'll continue talking about conduction equation. Okay, but this time we'll talk about only steady state case. Okay, steady state heat conduction. So the objective of this chapter is to understand the concept of thermal resistance. Thermal resistance, I think this word is you are very familiar with this word, resistance. We have electrical resistance, now we'll have thermal resistance. Thermal resistance. In the coming slides, we'll identify what's the meaning of thermal resistance and its limitation, and develop thermal resistance networks. Okay, and I think also you are familiar with resistance network, especially if I mention that these networks may be parallel resistance or series resistance or both combination. Okay, so yes, I think you are familiar with this. But now we'll talk about thermal resistance network for a practical heat conduction problem. Okay, so we'll talk about conduction as well as we'll talk about convection and radiation. Solve steady. So this is the first assumption or first condition. Our equation will be steady conduction problem that involve multi-layer composite. Okay, it's not simple. So composite, multi-layer, more than one material for three coordinate system: rectangular, cylindrical, and spherical geometry. Develop an intuitive understanding of thermal contact resistance. Thermal contact resistance. So this is the first time we are talking about this terminology, thermal contact resistance, and circumstances under which it may be significant. We'll see when we can consider this or when we ignore it. Okay. Identify application in which insulation may actually increase heat transfer. So insulation, what's the purpose of using insulation? العزل. Insulation is important to minimize heat transfer, but so its the essential use is to minimize للتقليل من انتقال الحرارة. عازل. Okay, so there is certain application in which those insulations may actually increase, not decrease, increase. So we'll see when we'll use insulation in a bad way that will result in increasing heat transfer. Analyze fence surfaces. Fence surfaces. So the meaning of fence surfaces, if we have a surface and surface like this, okay, so if there is extended sheets like this. ممكن نكون لحمينها لحام، okay. أو ممكن نكون مثبتينها ببراغي extended surface. Okay, this is one type of fence. We call it fence surface. Okay, and assess how efficiently and effectively fence enhance heat transfer. So the purpose of adding extended surface is to increase heat transfer, because we are increasing the surface area. Okay, so we'll learn how this surface, or how to calculate the efficiency and the effectiveness of mannequins. Solve multidimensional practical heat conduction problem using conduction shape factors. If the time allowed, then we'll cover this objective. Okay, now let's start with the thermal resistance concept, and we'll start with the conduction thermal resistance. Okay, so the conduction Fourier law, conduction in the wall, K multiplied by A multiplied by T1 minus T2 over L. Okay, remember this is Fourier law. And we can write the Fourier or conduction equation in this format if we assuming what? Let me go to the writing board. Okay, so R conduction, or Q conduction, sorry, equal minus K A dt over dx. So we mentioned in the previous chapter that we need to go further step in order to find out delta t over delta x. Okay, but if we assume, remember when we assume one steady state, two k constant, what else? Steady state, k constant, n equal to 0, this is wall, 3, 4. What is the other assumption? 1D problem. Okay, 5, D, or the boundary condition specified temperature. Okay, then we can directly write that this equation, or Fourier law, Q conduction will equal minus K A T2 minus T1 over L, and this bracket give minus sign, so minus with minus become positive. Okay, delta T over delta T, sorry, over delta X. This is the Fourier law. Q conduction equal to minus K A T1 minus T2 over L, and this bracket give minus sign, so minus with minus become positive. Okay, so here is the new equation. So Q conduction equal K cross-sectional area over L T1 minus T2. Now this term now we'll give it a new name. This is equal Q conduction equal T1 minus T2 over R conduction. For whom? For the first coordinate, which is 1. Let me go back to the slide. So we can write this equation, yes, after writing the assumption. Steady state, 1D, specified boundary condition, specified temperature boundary condition, and K constant. So we can write it directly like this. And in the whole chapter, we'll write it, and the assumption will be the same. Okay? Now, how to move from this format to this one? By assuming L over Ka equal to R wall or the reciprocal. So let us see here. So R wall from this equation, always we write it like this. Okay, R wall equal L over Ka for A. Let us check the units. So L meter, K thermal conductivity watt per meter degree Celsius or Kelvin. Let me write it Kelvin, multiplied by meter squared. Okay, so squared with meter cancel out, meter with meter cancel out, and we end up with Kelvin over or Celsius over watt. Okay, now if we substitute in here the unit for R wall degree Celsius over watt, and here we have degree Celsius, then Celsius with Celsius cancel out, and we end up with watt as a unit. Okay, which is the unit of Q dot conduction. Okay, let me erase everything. So the thermal resistance of the medium depends on the geometry. You can see here, this is the geometry, and the thermal property of the medium, K. Now, what is the physical meaning? Why we use thermal resistance? Why we call it resistance at the beginning? So resistance, if the resistance of the wall very, very high, what will happen to the Q? It will not pass because we have high resistance. Okay, there is no heat conducted through the medium because we have high resistance. طيب. Then when R will be very high, look here. So if K is very low, then R will be very, very high. When K will be very low, if we are talking about insulation, conductivity for insulation very low. It's not conducted heat. Okay, so its magnitude very, very low. Its property K, because K is a property, so K will be very, very low. Now, when we have high, if K is very, very high, conducted material, okay, then R will be very, very low. There is no resistance because this material conductive. So if R very, very low, we are talking about conductive material, then Q will pass through this medium easily because this material is conductive, like metal. This is if we're talking about K. How about geometry? The same. If we have L very, very large, okay, the thickness of the wall very, very high, then R will be very high, high resistance, and then Q will be very low. Like old houses in your village, okay, or old houses in a city. So بيوت العقيد I think بيسموها, I'm not sure. So thickness very, very high there, and you feel very colder, especially in summer, and in winter the opposite. Okay, so yes, geometry will affect the resistance as well as the heat conducted. Now let's see the analogy between heat or thermal versus electrical resistance. So you used to use this one RE, which means electrical, okay, and R sometimes we'll give it T, thermal, okay. So here, if we compare this to drawing, R, there is analogy between R and R, electrical. Now V1 and V2 delta V, we can say that those are the same, okay, delta T in the thermal, same as delta V in electrical. And here we have electrical current passes over the resistance I, this one, and here we have Q, okay. So heat thermal transfer Q dot بقابلها ايش؟ electrical current I, thermal resistance, the analogy is R electrical, and temperature difference delta T we have here on the other side voltage difference. This is analogy. And see, we use same symbols, resistance, okay, same everything. Okay, now let's talk about convection, heat transfer, which is Newton's law. Let me go to the writing board and we'll do the same. So Q dot convection equal to H convection multiplied by surface area multiplied by Ts minus T infinity. This is minus. Now, in order to write it like the conduction equation, delta T over thermal resistance, so I'll keep Ts minus T infinity, and I will write here R convection, where R convection equal to 1 over H area surface, okay? Yeah, here is the equation. Q convection equal H AS Ts minus T infinity. Or we can write it in the same format. Ts minus T infinity divided by R convection. Okay, where R convection equal 1 over H AS. And keep in your mind that the unit for the resistance, never mind if we are talking about conduction or convection or radiation, will be the same. Degree Celsius over what? Why? Let us check. So 1 over, the unit for H is what? Per meter squared Kelvin or Celsius, multiplied by meter squared. So meter squared cancel out, and we end up with Kelvin or Celsius over what? Okay. Now, the physical meaning. When the convection heat transfer coefficient is very high, is very large, when this value is very large, approach infinity, the convection resistance become 0, and Ts equal T infinity. That is, the surface offer no resistance to the convection. Why no resistance? Because R equal to 0. Where is it? Yeah, here. Okay. But let me go back a little bit. When H will be very high, when we are talking about convection. We said earlier convection There are two types or three types of convection: natural, force, sorry for bad writing, and phase change. Phase change, boiling or condensation. Phase change. Okay. Now the other question: which one has the highest H? Phase change, then force, then natural convection. Now, when H become very high, we are talking about phase change scenario. Then, so if this is very high, then this one is very low, very low. Okay, almost equal to zero. So here we are talking about very low value. So if we multiplied R with U convection, this value here will become very low, almost equal to zero, or it's equal to zero. Then we can say Ts minus T infinity equal to zero. As a result, Ts equal T infinity. Ts equal T infinity if we have very high H. Okay, what does that means? That means a Q can transfer here without any resistance because R equal to zero. This R almost not exist. Okay, because H very high and H R very low, then this value almost equal to zero. Then Q can pass easily. Okay, so that is the surface offer no resistance to convection, and thus it does not slow down the heat transfer. Nothing happened to Q. Q just flow in this direction without any resistance. Now, if we are talking about natural, no, the opposite. Natural R or H very low, okay, as well as R become very high, R very high, and then Q will become very low. So there is no Q, or there is a resistance for Q to flow. Now, radiation. Q dot radiation, the equation is epsilon multiplied by sigma multiplied by surface area multiplied by Ts to the power 4 minus T surrounding to the power 4. Remember, we write this equation in two formats, this format and the other one is, let me go back to the writing board. We need to write the three type of heat transfer in the same manner. So this is Q radiation. The other format is H radiation, AS, Ts minus T surrounding. Then I need to keep every time delta S divided by R radiation. Okay, where R radiation equal to 1 over H radiation AS. Yes, and the unit the same. Okay, we call it radiation resistance. For whom? For a war, because we are talking about radiation heat transfer coefficient. This is as a reminder to refresh your mind. This is the magnitude of H radiation and how we can calculate from this equation we did earlier in chapter 2. Now, in the surrounding, beside on one side of the wall, sometimes we'll encounter both Q convection and Q radiation. So we have two resistance. So those resistance will be on parallel. Okay, parallel as you can see. So Q flow, one of the Q flow or have a resistance from Q convection and another resistance comes from radiation. So the magnitude of Q, which is the analogy of Q is I, the same current, will separate one from there and one from here. So the total magnitude equal to the summation. Remember when in chapter 2 when we talk about combination, so the Q total equals summation of Q convection plus Q radiation. Okay, so we have two resistance on parallel. If we have two resistance on parallel, then the R total will equal to, let me write it here. So if we have two resistance on parallel, I believe that you know very well how to write it. So R total equal to 1 over, if this is R1 and this is R2, 1 over R1 plus 1 over R2, or you can write it directly, the multiplication over, but I need you every time to write it like this in general form, because sometimes we have three resistance on parallel, so you have to know how to write it like this. Type. So when T surrounding, this is the assumption when we do the combination, we assume that T surrounding almost equal T infinity, then we have H combined, which is the summation of H convection plus H. We did this earlier. Okay, that's it for this lecture. I'll post another lecture for thermal resistance network. Thank you for listening.